Okay, so here we are with the first cluster which hosts the first solution, and you can see these little schematics they have with each cluster in the book. Solution number one: bend the warming curve immediately by reducing short-lived climate pollutants and sustainably by replacing current fossil fueled energy systems with carbon neutral technologies and by extracting carbon dioxide from the air and sequestering it or repurposing it for commercial uses. This repurposing is already happening to some extent, but it's only happening to force out more oil from the ground by pumping CO2 into the oil rigs. Oil wells. The terminology here frequently used is with respect to CO2 emissions. Low carbon refers to energy sources that emit substantially less CO2 per unit energy than conventional fossil fuels. Solar, wind, hydroelectric, nuclear power fall under these categories. They are not completely carbon neutral because to produce these, there is carbon involved, right? So fossil fuels are used in the production and transportation of the products used in solar cells, wind turbines, and nuclear plants. So they're not zero carbon. Zero emissions, on the other hand, refer to energy sources or systems that truly have zero associated emissions of CO2 and other greenhouse gases. This is an ideal that is not realized by any current energy sources, including solar, wind, hydroelectric, nuclear, but could be approached as associated emissions from manufacturing or transportation systems approach to zero. So there is something called life cycle analysis, where you take anything, let's say a bottle of water or bottle of juice. It has the bottle, it has the cap, it has the fruits that go into it, manufacturing of the juice, sugars, other chemicals added, transportation, and so on. So you take end-to-end analysis of everything in terms of the carbon footprint associated, and then you determine whether that's carbon neutral or zero carbon and so on. So right now these low carbon sources can head towards zero carbon if we begin to reduce the associated carbon footprints involved in the manufacturing and transportation of these energy sources. Renewables are energy sources that are replenished naturally. I think you all know that already. Solar, wind, hydroelectric, geothermal fall under this category. So if you think about solar, wind, and hydroelectric, they're all essentially derived from solar energy. Solar energy gives us the equator to pole temperature gradient, which gives us the weather and climate, which gives us the wind, which gives us the rain, which gives us the rivers, and so they're all related to solar in some way. Geothermal is not. Okay, so that's just a little distinction you should be aware of. Carbon neutral refers to energy sources or systems that absorb as much CO2 as they emit. Energy source that is derived from fossil fuels can still be carbon neutral as a whole if the carbon released is captured and stored indefinitely. Okay, kind of a geologic time scale, millennia to millions of years if possible. Okay, so those are the issues to remember. Here are the negative emission technologies that are coming in various forms now. We won't go into details. Ocean fertilization is an idea that there are places where certain nutrients like iron are deficient, so if you drop iron into the ocean, more photosynthesis happens and it can take up additional carbon. But already experiments have been made, and this turns out to be not a net exporter of carbon, because the phytoplankton that is produced by photosynthesis has to sink out to the bottom of the ocean and get sequestered for geologic timescales. It turns out that that doesn't necessarily happen. There are details which we won't go into, but right now iron fertilization is essentially banned. Okay. Ocean alkalinity addition, so you can tinker with the ocean's acidity, alkalinity related, to make it take up more CO2, make it a more efficient sink. Okay. Accelerated chemical weathering, on geologic time scales. Rainfall dissolves CO2, produces H2CO3, and washes out calcium carbonate and silicate from the rocks and soils and puts it into the ocean, gets sequestered for a long time. There are methods by which you can accelerate weathering, like grinding them up and sprinkling them. Again, not demonstrated at scale yet. Manufacturing carbonate minerals using silicate rocks and CO2 from the air, so you take out CO2 that way. Direct CO2 capture, which is already being attempted in several places. Biomass energy with wind, with carbon capture and storage, so that's taking photosynthesis, which is taking out CO2, using it as bioenergy and not letting the CO2 back but sequestering it. You can see that they all seem to want to dump it into the ocean. Experiments have been made to dump liquefied CO2 into the ocean by places like the Monterey Bay Aquarium Research Institute. Again, not tested at scale. Remember the amount of carbon that has to be drawn down. That's not small amount, right? Or you can put it into various salt mines and old oil wells and other geologic faults where CO2 can be hidden for a long time. So afforestation and reforestation takes out CO2 here, gets used as biomass, and so on. Okay, these are called negative emissions because they take out net CO2 from the atmosphere. To get an idea of where we need to get to hit the emissions, okay, zero emissions by various timelines, various models have been run. These are called ESMs, or Earth System Models. So they have climate, they have vegetation, they have other human activities. So there is feedback between carbon and vegetation, ocean uptake, land uptake, and so on. And they try to do the whole Earth system. They come with various sophistication or complication, you can say. That's why you have a range here. Many models are run. You can see few models here. So the mean and the range is given for these models, and here is the ensemble of all those models, and the thin lines here are various simulations by these models. When you make future simulations, you have to assume, as I said before, things about population increase, technology, renewable sources, energy demand, food production methods, technology to take out carbon, and so on and so forth. So here is the historical emission from 2000 to, let's say, 2018 or so when this was done, and then future drawdowns. And you can see that fairly rapid drops are required, and then it stays into the future out to 2300. Okay, these kind of estimates are made, and these are the uncertainties that make us say that setting deadlines about how many years we have left to take out carbon can be kind of not a good idea in terms of unintended political, socio-economic, and social consequences. Okay, or even just credibility. What happens if these numbers don't mean much? Setting a deadline of 2030 and then 2030 looking the same as before, then it'll be a problem. Okay, nonetheless, that's solution one with some context. We'll come back to these again.